Oxygen. We need it to be alive, yet it's toxic to other forms of life. So as humans ponder and scientists research our most profound questions, are we alone in the universe? Has life occurred anywhere else beyond Earth? Is there life on exoplanets? Great attention is being focused on biosignatures, something that indicates or suggests the presence of biology indicative of life. Tonight, we explore oxygen as a biosignature. Good evening, good morning, and good day, and welcome to our June 2021 SETI Talks discussion. SETI Talks is the monthly lecture series produced by the SETI Institute here in Mountain View, California. I'm Steve Bordeaux. I'm the Deputy Director at the SETI Institute and the Director of Development. The SETI Institute is a nonprofit research and education institute whose mission is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe and to share it with the world, like we are tonight. Our SETI Talk series has been running for more than 10 years. And if you visit the archive on the Institute's YouTube channel, you'll discover hundreds of lectures, debates, and panel discussions featuring many of the world's foremost researchers, educators, and explorers in space science, covering an extraordinary range of topics. Some 16 months ago, the pandemic forced the conversion of SETI Talks to a virtual format. But that has given us the opportunity to reach a global audience, and we're delighted to have you all with us this evening. I'd like to welcome our registered guests on Zoom and also say hello to everyone joining from all our other platforms. As our regular attendees know, we love to find out where you're joining us from. So if you're on Zoom, use the chat function or add a comment on Facebook, Twitch, Twitter, or YouTube to share where you're tuning in from. We've attracted people from all 7 continents numerous times. And if you are the person tuning in from McMurdo Station again, share something only a true Antarctic researcher would know so we can dismiss the doubtful. We will have audience questions after the moderated discussion. If you're watching via Zoom, post your questions using the Q&A feature you see at the bottom of your screen. My colleagues will be fielding your questions and we'll do our best to answer as many as we can. Before we get started, just want to make you aware that we have our July SETI Talks is going to be on July 21st, and the topic is Rogue Planets and Opportunity for Life. And it'll be at 11 a.m. The regulars will know that sometimes we have SETI Talks earlier in the day to accommodate our speakers. Our guests will be introduced by our moderator for tonight's discussion, Simon Steele. Simon is our own Senior Director of Education and STEM programs, an observational astronomer himself with over 25 years of experience as a science educator, having held lectureships at Harvard University, University College London, and University College Dublin. Welcome, Simon.
Great. Thank you very much, Steve. Good evening, everybody. I'm looking down the list of where people are tuning in from. We've got Berkeley, we've got Charlotte, North Carolina, we've got Lima, Peru, Ontario, Japan, and I did see Syria as well. So welcome everybody from literally around the world. So biosignatures. Biosignatures, the fingerprints of life on other planets in our solar system or exoplanets could be the easiest way for astronomers to prove that we are not alone in the universe. And oxygen has been for decades the top contender for providing or proving that life could exist elsewhere. But how useful or how definitive is oxygen as a biosignature? In Earth's history, oxygen exists as a byproduct of photosynthesis by plants, algae, cyanobacteria. With the fast growth of exoplanets as a field and the development of extremely large telescopes on the ground and in space, we could soon detect oxygen signatures in the atmospheres of other planets. But will that signature actually mean that we've detected life? Present-day modeling of exoplanet chemistry is currently poking holes in the atmospheric oxygen means life scenario. So in terms of sign of life, has oxygen breathed its last breath? So to answer or perhaps address some of these questions, I would like to introduce tonight's 2 speakers. We'll start with Jade Checlair. Jade is a planetary scientist at the University of Chicago, where she's currently completing a PhD. Her research interests broadly include the modeling of the atmospheres and climate of habitable exoplanets and simulating future observations to detect extraterrestrial life. Her current work focuses on developing statistical tests of habitability that could be carried out with future NASA direct imaging instruments. In particular, she's interested in testing the concept of the habitable zone and its boundaries by using large numbers of exoplanets. Previously, she worked on studying the climate of tidally locked planets orbiting M-stars. We'll find out what M-stars are in a minute. Notably, she showed that they're not expected to jump in and out of globally glaciated states, as Earth-like planets may well do. So welcome, Jade. I'm going to introduce Josh as well. Joshua Krissansen-Totton is a planetary scientist and astrobiologist at the University of California, Santa Cruz. His research focuses on modeling the atmospheric evolution of rocky planets to anticipate exoplanet biosignatures and false positives. Joshua's research interests also encompass modeling the co-evolution of life and the environment to better understand the early Earth. And in 2019, he was elected as a NASA Sagan Fellow. So welcome, Jade and Josh, and I'm going to hand over the microphone to Josh to take it away.
Great, thank you, Simon. Let me just share my screen here. All right, well, thank you all for tuning in. I'm really excited to be here. I just want to give a short, an introductory talk on the topic before we dive into the discussion. And I want to start with this question: how do we actually search for life on exoplanets? A lot of the ideas we might have for life detection in the solar system, going after microscopic traces of life, microfossils, this is of course not directly applicable in the exoplanet context when we're talking about life detection across vast distances. So instead, what we're really trying to do here is looking for the byproducts of life. These are the only things that are detectable at interstellar distances. And so the search for exoplanet biosignatures is really the search for environments that have been modified by life in a way that's really obvious. And so broadly speaking, there are three types of biosignatures, three categories of exoplanet biosignatures, that is. The first are gaseous biosignatures, which is mostly what we're going to be talking about today. The waste products of metabolism, the gases that life produce, can build up in a planet's atmosphere and modify the planet's atmosphere to the point where it could be detectable. Oxygen, of course, being the prime example. But you can also imagine widespread life modifying the surface of the planet. And so if you had life with interesting pigments spread across the planet, then you might be able to detect this remotely. And we can also think about temporal biosignatures, so signs of life which imprint a time-varying signal in the planet's properties. And so this, of course, is Earth's CO2 increasing as we burn fossil fuels, but overprinted on that is this annual going up and down of CO2 due to the growth and die-off of northern hemisphere vegetation, a signal that's hard to explain without a biosphere. Now, when talking about biosignatures, particularly oxygen as a biosignature, a question I often get asked is, well, why are we so focused on Earth-like life? And what about really weird kinds of life? Why oxygen? And the reasons for, this is always a good question to ask, but the reason for the focus on oxygen is more than just, well, plants make oxygen, so let's look for that. You can actually make a reasonable argument for why oxygen is particularly compelling. Despite only having a sample size of 1, we think we know some things about life that are universal. Life needs a source of free energy. Photons from a star are always going to be a good source of energy. Life needs some kind of liquid medium, and so it's really difficult to make solid state life or gaseous life work, and so some kind of liquid seems to be necessary. Water is going to be the most abundant, perhaps the best to use. And then, as fun as it is to imagine exotic subsurface biospheres elsewhere, living off eating rocks or something like that, these are unlikely to modify the planetary environment on such a massive scale that we could detect it from light years away. And so we're looking for really productive biospheres. And so all of this leads us towards photosynthetic life. Of course, there are lots of ways you can do photosynthesis. Oxygen-making photosynthesis is particularly compelling for additional reasons. So here's a version of a chemical reaction you probably saw in high school, a crude representation of photosynthesis. You take as input CO2 and water. With light, you can convert that to oxygen and biomass. And the interesting thing about oxygen making photosynthesis is that all you need is CO2 and water. These inputs are virtually unlimited on a planet's surface, unlike lots of other kinds of photosynthesis where you're limited by how much iron's around or sulfur or hydrogen or something like that. And so if life can evolve this mechanism, this oxygen-making metabolism, then it's likely to dominate the biosphere and potentially accumulate in the atmosphere. And then finally, oxygen is really reactive. And so this is kind of the key argument behind the case for oxygen as a biosignature, is that it doesn't hang around, it reacts with stuff. And so if you see it in the atmosphere, it's got to be replenished continuously, at least under most circumstances. With that said, there are a number of scenarios people have suggested for how you might build up oxygen in a planet's atmosphere without life. And we'll probably go through these in more detail later on, but it's just to say people have thought about the chemistry of atmospheres and thought about the ways in which uninhabited planets could build up oxygen, but also the clues that might alert you to the fact that that was the kind of planet you were looking at. So to return to the original question then, how do we search for life on exoplanets? It's really about looking for the byproducts of life that build up in a planet's environment. And then once we've identified potential biosignatures, carefully think about all the ways we could be fooled, all the non-biological processes that could produce those signals. And then once you're confident you've done that, actually think about how to do the observations and the very difficult, astronomical task of getting that data and interpreting it. So with that, I will hand over to Jade.
Me going to full screen. Okay, thank you, Josh, and thank you, Simon, and hi, everyone. It's great to meet you and to be talking to you today. So to get right into it, the future of exoplanet observations is very bright and exciting. And some of you may have already heard of some of the names of these missions here, some of which we hope will help us characterize the atmospheres of exoplanets. In particular, I want to draw your attention here to James Webb Space Telescope, which may help us characterize the atmospheres of planets orbiting close to M stars, so small red stars. And then even more exciting, in my opinion at least, are next generation telescopes such as LUVOIR and HabEx right here. So these two, we hope, will help us characterize the atmospheres of Earth-sized planets orbiting in the habitable zones of sun-like stars. So this means they might help us characterize Earth 2.0, which is very exciting. Oops. Okay. So with these instruments, like Josh mentioned, we hope to detect biosignatures, such as oxygen, to indicate the presence of life. So this is, of course, a huge goal in astrobiology. And if we do detect convincing evidence of oxygen on an Earth-sized planet orbiting a sun-like star in the habitable zone, we will definitely be popping champagne. This would be a huge discovery. But I think we have to keep in mind that it might be more difficult than we hope to detect those biosignatures. So some reasons for that are the possibilities of false negative and false positive scenarios, which Josh mentioned shortly. Another reason is the diversity of exoplanets. So we expect exoplanets and their atmospheres to be very diverse, but this makes it harder for us to really plan our interpretations of observations because we may not know exactly what we're looking at. And then, of course, the missions are very promising, but they will have their own limitations. So, for example, we may not be able to detect lower amounts of oxygen, particularly on planets that are further away. And of course, there's also going to be some observational noise in our observations, which may make it difficult for us to know if we're even detecting a specific gas. So because of all those reasons, it's not the ideal scenario, but it's a possibility that we could end up with no convincing evidence of either oxygen, or if we do find oxygen, we may not know that it indicates the presence of life for certain. Now, this possibility should also motivate us to find other ways to use this search for biosignatures with future telescopes. And one way to do this is to use the many exoplanet detections we'll have to test some theories of habitability. So far, we've been making a lot of assumptions for these Earth-like planets based on Earth history, and we haven't really gotten to test many of those. And now those future instruments are going to allow us to look, hopefully, at a lot of planets potentially similar to Earth. So this is really a new opportunity that's being afforded to us, which I think we should take advantage of. And to give you an example of what I'm talking about here, one question we could ask is whether exo-Earths are likely to be Earth-like. So you may have heard of the term exo-Earth before, but here, just to clarify, we mean by exo-Earth an Earth-sized planet orbiting in the habitable zone of its star. So the habitable zone means that it could potentially have surface liquid water, but it's not a guarantee, it's a possibility, okay? It's neither too hot nor too cold. And it doesn't really make any assumptions about what's in the atmosphere of those planets. And we want to know whether these exo-Earth that we hope to be detecting are likely to be Earth-like. Now here, an Earth-like planet would develop Earth-like life that progressively oxygenates its atmosphere, so adds oxygen to the atmosphere of the planet, like what happened on Earth. So on Earth, we believe life evolved at around 4 billion years ago, right at the onset of the Archean here. So before the Archean, we were in the Hadean and there was no life. Then life evolved to enter the Archean. However, as you may see on this plot here, this is oxygen versus time. So 0 is the present, this is the past here. The oxygen was really low in the Archean. The reason for that is we believe oxygenic photosynthesis that Josh introduced did not evolve right away. Okay, so oxygen was very low, then eventually it increased up to modern levels. Now, if we were to observe a modern Earth-like planet with those telescopes, we would likely detect oxygen on it because it's high enough. For this kind of intermediate Proterozoic Earth, we may be able to if the planet is close enough to us. But for an Archean-like Earth, this is a great example of what we call a false negative, because we know that planet has life, yet we may not detect it because we wouldn't see any oxygen on it. Okay, so that's a false negative, and it's another potential complication with searching for life and biosignatures in general. So before I end my talk here, I want to leave you with something to think about, which is going to tie in to the poll that Simon is going to give you afterwards. So my question is, will we ever be 100% certain that we have found life by detecting biosignature gases like oxygen? So if you think the answer to this question is no, maybe because you think that there's so many false positive scenarios and maybe we don't even know all of them yet, so how can we be sure that it's life? Then what do you think would be convincing evidence that we have indeed detected life? Maybe you think we need a high definition photo of the surface of a planet and we could potentially see vegetation, which would be evidence of life. Or would we need a flyby mission, like a probe like Juno here around Jupiter, which could better characterize the atmosphere of the planet, but also, of course, take this high definition photo? Or do we need a lander mission like Curiosity on Mars here to analyze the rocks and potentially detect microbial life if it exists? Or do we need a return sample mission? So do we want to bring back a sample from that planet and look at it with our own eyes in our labs? Now, I have to point out that these scenarios here are currently unrealistic. They're science fiction. Okay, so the closest habitable planet, potentially habitable planet to us is around 4 light years away. So we can't yet send anything to it, unfortunately. But regardless, I'm interested of your opinion on this, and that'll be in the poll later. So that's it for me. Here's my email if you want to ask more questions. And thank you.
Thank you both, Jade and Josh. And of course, we're gonna force you to give us your feelings on your optimism for this this question towards the end. There are almost as many people tuning in from around the world as there are exoplanets at the moment. So I can't really go through everybody, but we got people tuning in from Puerto Rico, Minnesota, Toronto, Hawaii, Sri Lanka, Pacifica, just up the road, Louisiana, Argentina, Baja California, and I am going to stop there, otherwise we'll run out of time for talking about oxygen signatures. Maybe just start with Josh and talk about, the biosignatures and looking at a planetary atmosphere. Exactly what are you doing? And maybe this is for people who are not too familiar with the concept of spectroscopy and reading an atmosphere about what it's made of.
Yeah, sure. Actually, I have one extra slide on this since I thought it would be good to have a diagram. So essentially, what we're needing to do is separate the light of the planet from the light from the star. That's the really hard part. And we can talk more about how you might actually achieve that. But once you've got light from the planet, right, you can, a bit of help from Pink Floyd, disperse it into its component colors, wavelengths, and just look for the signature of different gases, because different gases in a planet's atmosphere will absorb light at particular wavelengths. So they leave a diagnostic fingerprint in the spectrum. And so this is just a simulation of Earth's spectrum and invisible wavelengths. And so a gas like oxygen absorbs very, very strongly in the visible. So that is kind of the goal, to look for these diagnostic absorption fingerprints, and then from the size of the feature, you can figure out, well, how much of that gas is there, and so on.
Mm-hmm. So you got, we see oxygen as a big dip there, and then we've got H2O, which is water in the atmosphere, which may or may not be relevant as a sort of secondary identification. You've also got O3 there, which is ozone. So what's the deal with ozone? Is that relevant to our search for life?
Yeah, definitely. So ozone is a byproduct of oxygen, right? So there's abundant oxygen in the air, then photochemical reactions between high energy UV light coming in from the star break up oxygen and create O3, which can then accumulate in the atmosphere. And depending on what wavelength you're looking at, what kind of instrument you have, in some instances can be much easier to detect than molecular oxygen, O2, or perhaps it's easier to detect it at lower abundances. So it's definitely something else we'll be going after.
Right. Jade, you talked about modeling atmospheres. Of course, all the exoplanets that we have discovered so far, we haven't actually seen. I mean, I think there's one or two that have a direct imaging, but most of them are inferred from the light curves of the star. And yet you want to tell us, or you want to find out what these planets actually look like. And how different they could be. We have a few planets in our solar system that we have a good idea about, but tell us about how you model a planet. What are your guiding principles for that?
Model a planet? Sure. Well, I think one way you can model a planet is using global climate model. If you want to see, what its climate could look like, what kind of gases you could end up with, and what their concentrations would be based on a certain situation, so how far it is from its star, and things like that. And those global climate models are basically based on the Earth in part. So we start out by the Earth, and then we change the conditions of that model to try and model other scenarios. So of course, there's things we don't fully understand, especially clouds, which could really alter, the climate of a planet, and of course our observations of it as well. And so that's there's some uncertainty in modeling these planets, but most of what I do is using those GCMs to model what their climate could look like based on the Earth, so really benchmarked to Earth.
Mm-hmm. So you've got your nice big space telescope or ground-based telescope, and you've got your signature, your spectrum from of an exoplanet. Maybe we're going to take this to Josh, and there in that atmospheric signature, that spectrum, are oxygen lines. You presumably would be reaching for a bottle of champagne, but maybe not for a bottle of expensive champagne that would indicate the winning of a Nobel Prize. Once you've made that oxygen signature discovery, what does that tell you initially, and what's the next step?
Yeah, that's the big question, which is I think going to be very relevant in the next few years. So here's the thing, right? There are all these scenarios that people have dreamed up for how planets could build up oxygen without life, and depending on the spectrum of the star and what the interior of the planet is doing and so on, people have been really creative in inventing these scenarios. But it's important to note that they are entirely hypothetical at this point, right? No one's gone out and found a planet with an oxygen-rich atmosphere inhabited or not. And so we don't really have any frame of reference yet, any verified frame of reference for what oxygen means. We just have all these sort of theoretical cautionary tales in how you might make oxygen. And so I think once you make that detection, what you're going to have to do is think about the context of that planet. Okay, what kind of star is it around? What do you know about the evolution of that star? What kind of fluxes is that planet being subjected to? What are the other constituents in the atmosphere? What does that tell us about the possible source of oxygen? Is the planet even habitable? That's something you'd want to independently verify, like see if you can see some evidence for liquid water at the surface or some other habitability indicator. So there's a lot of, I think that detection means that's when your work starts to really understand that object compared to all the other planets that you're characterizing at the same time.
Sure. So that's step one, is actually making the detection, and then the hard work starts. Yeah. Jade, we mentioned briefly in your introduction about M stars. Now, M stars are everywhere in the galaxy. They're these little red things that make up about half the stars in our Milky Way. There's a lot of them, and so therefore, it'd be nice if M stars were hosts to habitable planets. Say a little bit more about it. It seems to me that an M star is the last place you'd look for a habitable world. But can you prove me wrong on that?
Sure. I mean, we don't know yet whether, M stars are likely or not to host habitable planets. You're right that there's a lot of talk about them causing their planets, even if they're in the habitable zone, to completely lose their atmospheres early on. And so that would create a non-habitable planet, but we're not sure of that happening. So we'd need observations to confirm whether or not this happens all the time, some of the time, or if it's really rare. But if it is, if M stars do have habitable planets in their habitable zones, then there might be some difficulties also with biosignatures such as O2, because we have a lot more ways for O2 to be created by non-life around M stars than around G stars like the sun. So M stars are definitely complicated, but there's so many of them that, it might be easier to look at planets around them just from their number.
Mm-hmm. And a bit easier to discover the planets and get more information about them. Is that true as well?
Yeah, well, so I guess in the near future, the James Webb Space Telescope will allow us to look at planets orbiting M stars. It might not tell us everything about what's in the atmosphere of habitable zone planets, because they might be a bit too far away, but it's definitely, I guess, the nearest prospect for us to look at.
Okay.
Just to add to that.
Yeah, of course.
Yeah, we're basically stuck with M stars for the next decade, because that's all that Webb and the ELTs can really do for small rocky planets. So they have many problems with their habitability and biosignatures, as Jade was saying, but those are the objects that are the easiest to observe. So that's what we're going to look at. Good.
Yeah, take what you can get, I suppose. I mean, we do know one planet that has a wonderful oxygen signature, and we're sitting on it, and in that oxygen signature at the moment. I'm just wondering if say you had an alien civilization, let's say 20, 30 light years away, that have a nice telescope like their equivalent to the JWST or something bigger, and they're looking towards our solar system. What would they be able to tell their SETI talks about what they've discovered of the planets around our sun? From this distance, is it obvious that Earth has life? And what would you see, and what would you say these are the best pieces of evidence? Jade, do you want to take that?
Sure, I can start.
Yeah.
So I guess for Earth, Earth today has a lot of oxygen. So I'm pretty optimistic that with a good enough telescope, aliens would be able to tell that we do have oxygen. Of course, they would probably be wondering about potential false positives too, and think of all the potential scenarios in which we could have oxygen, but in which it would be not created by life. If they were able to detect other signatures such as methane, because we do have some methane here, then that could confirm that we're inhabited and send them to us potentially. But I think the issue is if they were looking at Earth in the past, then they might be looking at an Archean type planet, which has life and in which they would not detect oxygen, and they might cross us out really quickly thinking there's no life over there, potentially.
Well, I'm going to say, yeah, oxygen, I don't believe that. And the methane thing, I mean, they found that on Mars. I don't believe that. What's evidence piece number 3? Is there something else that you would detect from the Earth that would say, you know, I'm pretty convinced here? Josh, what do you think? I
mean, the extent to which the aliens are convinced depends entirely on how much money they want to spend on their telescope. Right? like if they really want to be sure, they could go after all the trace gases that are not just oxygen, but oxygen in combination with a lot of other gases like methane. And that combination of the two is very hard to explain without life, especially if both are very abundant, because you not only have to explain how the oxygen got there, but oxygen and methane don't play well together. They react together very quickly and destroy one another. And so the coexistence of both requires massive replenishing fluxes of both. And I think, you know, anyone observing Earth and seeing those gases together would be pretty suspicious that there was something interesting happening on that planet's surface.
A very compelling argument, yes, that something is going on. And then you just need to turn your radio telescope to us, I suppose. But I mean, there has been I don't know if it's a positive or false positive. You might want to comment. Of course, our nearest planetary neighbor, Venus, which is definitely an Earth-like planet in the sense that it's about the same size and almost the same distance from the sun, and yet it's something has gone, you know, very, very wrong or different depending on, you know, how you characterize Venus, and yet there was that detection of phosphine, which is a biosignature. It's not clear that this was a definitive observation, and so it's a false positive. Can you say a little bit about this observation? And I mean, is phosphine a good secondary piece of evidence?
I mean, if the phosphine was really there, that would be weird. But yeah, I think I'm not convinced at this point of the detection. This is going to be worked out in the literature. There's a big back and forth on, you know, whether the signal is real. So we'll see how that plays out. But I think Venus is really important from a biosignature perspective for other reasons. And this kind of goes back to what I was saying before about all our, you know, false positives for oxygen. These are all hypothetical scenarios, and we have this counterexample in Venus, and that Venus, an Earth-like planet, seems to have lost a lot of water. One of the ways that you could make a lot of oxygen is through water loss. You lose the hydrogen to space. You break up water, you lose the hydrogen to space because it's heavier than the oxygen. You leave behind the oxygen, and so you can imagine all these scenarios where hydrogen loss leads to a non-biological oxygen signal. But Venus doesn't have that. There's virtually no oxygen in the atmosphere of Venus, despite all the evidence of it losing its water. And so understanding what happened there, where did the oxygen go, I think that's going to be really crucial for interpreting oxygen detections on exoplanets. So from that perspective, yeah, I'm really excited about the upcoming missions to Venus and what they might learn about Venus's past.
Sure, and as you say, a planet doesn't sit unchanged in history, just as the Earth is an example. You really want to know what's happening to you know, at various stages in a planet's evolution. And we have that with the Earth, you know, reasonably well. But if these next missions to Venus could give us a history of another Earth-like planet, and how it evolves over time, that gives you another data point, doesn't it? Something else to model on, Jade.
For sure. Yeah. And we might know whether Venus was even ever habitable. It could have never been. So that would be interesting as well.
say a little bit more. We're going to pull up the poll in a couple of minutes, but you mentioned James Webb Space Telescope, which is going to be launched, we all think and hope, in October. But you also mentioned LUVOIR and another generation of telescopes, and of course that's looking a little bit more in the future. And you know, Josh mentioned money, and that's something else to think about, how soon that's going to be. But how do these next generation telescopes, how will they change how we see life and how we search for life?
Yeah, for sure. So the big thing with these next generation telescopes is they'll actually allow us to look at the atmospheres of planets that are the size of the Earth and orbiting in the habitable zone of sun-like stars. So that's not something we can do yet. And James Webb is going to look at planets that are usually a lot bigger or orbiting not inside the habitable zone. And so that's something that's going to be new with these next generation telescopes. And it's really nice because for oxygen, there's a lot less false positive scenarios around G stars. And so detecting oxygen, I think, around a sun-like star, a G star, will be a lot more convincing of life than around an M star. So that's really exciting. And the point is, with these instruments, they're going to be really large. And that's why they're so expensive, but they'll be able to tell us a lot.
Josh, what telescope are you looking forward to in the future?
I mean, anything that will give information on rocky planet atmospheres is very exciting to me, because that's not really something we've been able to do at all yet. The thing to know about Webb, it will give us some information, as Jade was saying, on rocky planet atmospheres, but you have to remember, this thing was designed like in the 90s, right? It's taken a long time to come to fruition. So this was not designed with exoplanets in mind.
It was designed about the cosmology, wasn't it?
Right,
really?
right.
Yeah.
It just turns out it's also very useful for exoplanets. And so it won't actually be capable of detecting oxygen biosignatures on any known targets. It might be able to detect really, massive oxygen atmospheres from hydrogen loss, but the comparatively small amount of oxygen that life produces probably won't be accessible to us. You might be able to do it with some of the ground-based telescopes. Instead, what it will do is look at kind of these exovenous analogs and be able to see, well, did they build up a lot of oxygen from non-biological processes? And that'll tell us about the usefulness of oxygen kind of going forward, thinking about these future missions like LUVOIR and HabEx. And I guess the other difference there is scale, right? Like if we put all the money into LUVOIR and go with the deluxe, whatever it is, 15-meter version, then we can maybe look at 50 potentially habitable planets, which is a meaningful sample size.
Yeah.
Actually, maybe Jade wants to say more about that, since you've thought about these kind of sample size issues with LUVOIR and HabEx.
Yeah, so these types of tests of habitability that I was mentioning really require a large sample of planets, and so are really only feasible with an instrument like LUVOIR. HabEx is a bit too small. It's really great because it will be able to look at the same types of planets and at the same gases in their atmospheres, but it'll just be able to look at less of them. That's the big difference. It's how many of them it'll be able to detect. And so there's a big price difference, of course, but I think if we're going to build one of these instruments, might as well go all out, build LUVOIR, get a bunch of data for a very long time, keep us occupied, then we can move on to other things for a little bit, but yeah.
Okay. That's a plug where the SETI Institute has no input into the LUVOIR telescope, alas, but who knows, maybe that'll change. I think it's time maybe to bring up the poll, and we'll have a look at this. And while we have a look at this, I'd like to invite everyone in the Q&A to jot down your questions, and in a bit we'll turn over the microphone to Frank Machis and Beth Johnson to ask those questions. But Lee, can we have the poll, and let's have a look at, see if we'll get your opinions.
Unfortunately, Simon, Lee's internet has gone down and he is not able to send a poll out. So you can go ahead and put your opinions in chat, and that's unfortunately as good as it's going to get tonight.
Okay. That's such a smooth professional outfit we have here. Oh, poor Lee. But yes, definitely put your questions in the Q&A and put your opinions in the chat. See if we'd like to know your opinion on whether this is the way we are just going to discover life elsewhere. Can we trust oxygen? Just like can we trust water as a guide to life, or are we barking up the wrong element here? So have we got some questions, Frank and Beth, to ask the panelists?
Yes, we have a lot of questions, and since we have no poll, we're going to take time to answer to even more questions. So it's a win. Yeah, so one of the first questions we got is, it's a very technical question, but I want Josh and Jade to take the time to answer to that, is how do you separate the star light, the light of the star from the exoplanet? What is the technique being used to do this? And why do we need to send space telescopes to do that? And this is a question by Floyd and a lot of other people.
Sure. I can start, or do you want to?
No, go ahead.
All right. So there are a few ways you can try and separate the planet's light. What is being done to date is basically letting nature do it for you. And so that is when a planet happens to transit relative to how you're looking. If it passes in front of the disk of the star, then you don't have to do any work to separate the star's light from the planet's light, because you get the planet backlit when it's in front of the star relative to you, and not when it's elsewhere in its orbit. And so by subtracting those two, you can isolate the light from the planet effectively, or the signatures from the planet, and do it that way. Of course, comparatively few planets pass in front of their star relative to how our viewing perspective. And so if we want to do this for all planets, you need to block out the light from the star, physically block it out somehow. And so there are a few ways you can do that. You can put your telescope in space, and you literally put a disk like a few tens of thousands of kilometers away and block the light from the star, and just leave behind so you can look directly at the planet light. Or you can basically take that disk and put it in the optics of your telescope. And there are pluses and minuses of doing it each way. In general, it's easier to do these things in space just because the atmosphere is creating a lot of problems if you're trying to do that from the ground. Although the ground-based ELTs will be able to go after transiting Earth-sized planets and potentially see oxygen biosignatures on those planets. So that's it in a nutshell. Did you want to add anything, Jade?
Sure, I guess I could talk about the star shade concept. So one of the instruments I mentioned, HABEX, has this really awesome concept where instead of using a coronagraph, so inside the telescope itself, if we have a star shade, which is separate from the main part of the telescope, and it kind of looks like, sort of like a flower, essentially, with petals, and that star shade would move away from the telescope to hide different stars. So we'd be able to adjust it, and it would be really, really efficient. It's sort of like a coronagraph on steroids. It would be very efficient at hiding that starlight so that we can look specifically at the planet. So that's a really exciting new concept that comes with HABEX.
So our next question is from Jim, who asks, can we look back at Earth from one of our distant spacecraft and see what we would detect?
Do you want to take this, or I? So this has been done. This is a great idea, and it's been done with several spacecraft. Carl Sagan actually famously did this in the 90s, looking back at Earth, and wrote a really fun paper that's like from the perspective of aliens trying to figure out if there's life on Earth. And so this is, yeah, the brief answer to your question is this is an area of study using all sorts of different spacecraft with different viewing angles and different distances to try and figure out what can we actually learn about the Earth as kind of an exoplanet analog. And yeah, I mean, you can see the biosignatures. It seems to work.
Okay, we have another question here by Hazi. Were there a signature that may suggest life will be there in the future? For example, viewing us as an Archean planet, will there be an indication in the future that what will come to be? meaning that could we basically infer from a past indication of signature of life what the planet will become in the future?
Or could we guess the evolution of the planet based on potentially
On the
seeing
present,
an Archean-like
yes.
planet? I mean, we could try to go through different scenarios, but I think we wouldn't know exactly how that planet might evolve. I think it might be random. We're not even sure if every planet evolves like the Earth does. So it would, I think, at this point be hard to say exactly what will end up of a planet, even if it looks like an Archean planet. It's possible most exo-Earth are stuck in an Archean-like state forever. We're not sure yet. Maybe the Earth is special, or maybe it isn't.
Thank you. Josh, do you want to add something about this?
No, that's good.
So our next question comes from Louis. What does it mean to find a twin planet that would be strictly identical to the Earth? How much similar to the Earth would an Earth-like planet need to be to develop any life that would be somewhat identical or on the same scale as the life we have here now?
I think that's a really tough question to ask when you just have the one instance of Earth evolving and the one instance of life. The term like Earth twin is kind of used loosely to mean different things in different contexts. Sometimes it can mean just a Earth-sized planet around a sun-like star, but usually it means something that's more Earth-like in its properties, perhaps even in how it evolved. But I mean, that's sort of what we're trying to do, right? To figure out to what extent do planets evolve in a predictable way, given if they start with the same conditions, do you get to the same end result? Is the emergence of life inevitable? Like, these are the questions we want to answer, but it's just the Earth to go off. It's really tough to know at this point.
If I can add something, I think a starting point to what we would think would be an Earth twin at this point would be a planet that's roughly Earth size, not exactly, but roughly around a sun-like star, so a G star, and in the habitable zone, because that means it may have surface liquid water. Then if we can tell whether or not it has liquid water on the surface, that'd be, I think we would probably call that an Earth twin.
Okay, so we have another question here, specifically addressed to Joshua by M.A. Pilizzari. Can you please describe one or two of the many scenarios for putting abiotic oxygen in the atmosphere? Which are the most theoretically compelling?
Sure. So there's kind of two broad categories, I guess. And one I already talked about. It's if we've got water in the atmosphere, you're breaking up the water from high energy radiation, losing the hydrogen, leaving behind the oxygen. And so oxygen can build up that way. The other way you can do it is not necessarily through losing a lot of hydrogen, but just from a lot of UV light breaking up CO2 into carbon monoxide and oxygen. And if you break up CO2 faster than you can put it back together again, you can start to build up oxygen that way. And so within those two broad categories, there are all sorts of subcategories of ways that make hydrogen loss more likely, or scenarios where the CO and the oxygen don't recombine. I would say that the one that people worry about the most, kind of in the era of James Webb, is the fact that these small stars we talked about, the ones that are most easily observable with Webb, they are very bright early on for a very long time. They take a very long time for to kind of cool off and start on their main fusion sequence. So what that means for planets around these stars is that if we observe them today and they're in the habitable zone, they were subjected to maybe 1 billion years of really being irradiated, but they could potentially have lost a lot of hydrogen and left behind a lot of oxygen. And so the warriors will look at one of these habitable zone planets and find oxygen, but it'll be this leftover from being roasted early on. And so that's, yeah, we'll see if those planets exist quite soon.
So Jade, this question is for you. Are moons on exoplanets also being explored? In our solar system, the moons of our gas giants are possibly habitable, but not in the so-called Goldilocks zone. That question is from Carol.
Yeah, that's a great question. We already have trouble observing the exoplanets and knowing what's in their atmospheres. So I think moons of exoplanets are going to be a next step in the future because they're just so much smaller. So it's definitely possible that a moon could be habitable, could have water potentially, but they're just so small usually that they're going to be really, really hard to see because we're really, really far away from all of those exoplanets. So it's hard to resolve them essentially.
Okay, so we have questions about M dwarf stars specifically here. And of course, I can find my question. Oh, yeah, I have it now. Have you developed a model, an accurate model of the impact of X-ray, UV, and solar wind on the atmosphere of exoplanet? And what can we say about biosignatures after studying this kind of models and the impact?
I could start. So yeah, this is a lot of people thinking about this, trying to model the way in which the unique spectra and the particle fluxes from these small stars affect an atmosphere, not just in how they strip the atmosphere and the gases that are lost to space, but also they affect the chemistry of the atmosphere and the molecules that get broken up and recombine. And so, yeah, it's hard to summarize such an immense topic with people working on different aspects of it. I would say that with regards to the biosignature question, well, there are various problems, right? We don't know if these planets can even hold on to atmospheres, given the way in which their stars could erode the atmospheres. So that's kind of the first worry that people kind of model and make predictions about, but we won't know until we look. And then on the biosignature side, there's the early hydrogen loss where you could build up oxygen, like I talked about, and all the ways in which the chemistry of an atmosphere could be changed by the stellar environment, which could mimic oxygen as a biosignature through breaking up CO2. So yeah, I guess the answer to your question is people are trying to model these things as best they can without any data yet on how these planets work.
And I think if I can add something that's really interesting is some people are also trying to see whether planets around M stars that could have lost all of their atmospheres, like Josh mentioned, could potentially regain it. And so those would be called zombie planets. So even though they might have lost their atmosphere early on, they could potentially outgas a whole new atmosphere. And so all of that is, as Josh said, an active area of study, and it's really exciting.
So our next question, we have a lot of great collaborations going on internationally, especially in the last few decades. Is there any particular reason why we're not trying to create some really excellent 1 or 2 telescopes instead of all these smaller missions?
There certainly are collaborations that go on with a lot of these instruments, especially the ground-based telescopes are often multi-funded by many, many countries, both private institutions, public institutions. So that does go on. But for the LUVOIR type missions, like that's serious money. It's $20 billion. And so even with a broad international effort, like these aren't easy missions to fund.
Yeah. I think there's one mission called LIFE that's really exciting, and that's a big international collaboration that could look at those habitable zone planets orbiting G stars, and also look at some biosignatures in the infrared, like ozone and methane potentially. And that's an international collaboration. So I think there's definitely a future for those big collaborations. It's hard based on bureaucracy and of course money, who pays what, who gives how much money, who gets the most benefits. It's just a real headache. And so that's why usually they're maintained within each country, and politics are complicated, but it's hopeful, I would say.
Okay, so this is the last questions we got. So Simon, it's okay if I ask this one?
You go right ahead.
Okay, so what's your opinion about the possibility of inorganic life forms? Just to elaborate, if a civilization has transitioned to a computer-based conscience, it may not require oxygen anymore. So how will we detect it? Do you think about these kind of things?
It's certainly an idea that it's fun to think about. And yeah, if intelligent life is common, right, that could be a very common end product. And so we should be thinking about what signatures that would leave, perhaps on planets that aren't even habitable by our definition, right? Because non-organic life doesn't have to live where the water is. I guess you would be looking at the obvious thing that springs to mind is some sort of infrared excess there. But maybe there are other planetary signatures that you could go after. I don't know. It's interesting to think about.
Yeah, I think people are talking a lot about techno-signatures. So looking at signatures specifically from a highly technologically advanced, I'm not sure if simply AI, but at least highly technologically advanced civilization. And so we'd be looking at aerosols that reproduce through industry, for example. Another thing we could do is look at a planet that's not in the habitable zone, but is weirdly habitable, because that means they found a way to engineer their own climate to remain habitable for a really long time, past the normal habitability of their planet. So that's something that we could potentially look for that would, tell us something about the civilization being really advanced.
Great. Yeah, maybe there's something. Hopefully we won't need that technology. Thank you very much. Just one last question. This is to poll you guys. Optimism or pessimism? Are you optimistic that within a certain length of time we will discover oxygen signatures, and are you optimistic that that will be the first step to the discovery of life on other worlds, or is this a step too far? Jade, do you want to start with this?
Sure. Yeah, I would say I'm optimistic that we could detect oxygen definitely on a planet, at least within our lifetime, within the lifetime of some of the younger people in the audience here.
Yeah, thank you. I won't respond to that
one. You're young. No, but am I optimistic that we'll know for certain that it indicates the presence of life? I'm not so sure about that one. I think that might take us longer. I think at the very least, searching for oxygen and finding oxygen will tell us which planets are intriguing, which planets we really want to be able to look at. And we might, then find the money put together, because that'd be a big motivating factor. If we think it's potentially inhabited, we could find a way to put the money together to maybe have a telescope that takes some sort of image of the planet to see, if there's vegetation or something like that. So that, I guess it could give us some really interesting targets at the very least.
Josh, optimist, pessimist?
So I don't have a strong opinion on how abundant life is. I just don't know, because that depends on how easy it is for life to get started. But if life is common, I'm pretty optimistic that we will find it and be pretty certain that we've found it. And I think oxygen's a good place to start. And I say that because, say we find oxygen, there'll be some ambiguities. We won't know for sure at first if it's life or something else. But you'll have a sample of planets you're trying to understand, you'll know, okay, what do I have to do next? What's the next telescope I have to build to disentangle that, true biological oxygen from not? And there are plenty of creative concepts out there for how you do that. For ideas where you put a telescope on the moon, or you go out and use the sun as a gravitational lens to get a beautiful image of these exoplanets. So there are definitely pathways to being sure. And so if life is common, I expect that we will find it and be pretty confident that is what we found.
And as you say, the discovery of an oxygen signet is just the start of the journey.
Exactly.
Thank you both very, very much. Thank you everybody for tuning in. This is being recorded, and it will be available to watch on our YouTube channel starting from tomorrow, I think. In the meantime, I'm going to hand proceedings back to Steve Bordeaux. Thank you very much, everyone.
Well, thank you, Simon, and especially thank you, Jade and Joshua, for joining us tonight. So even though we're not together in person, our guest speakers today will be receiving a mission patch from the SETI Talks series and the highly coveted SETI Talks mug. There's only one of these mugs for every speaker who's ever been a lecturer or panelist. So if you have one, you're special, part of a unique community. In fact, they're so rare, I don't even have one here to show you tonight. So in closing, I just would like to call out to some special audience members who've joined us tonight. While we're thankful to each and every one of you who tuned in tonight, we couldn't put on SETI Talks without the gifts from our supporters, in particular, our SETI Stars. SETI Stars are folks who enjoy the convenience and ease of making a monthly gift of support to the SETI Institute. So to borrow a phrase from NPR, it's thanks to viewers like you that we are here tonight. If you're not a SETI Star, it's easy. Hop on over to SETI.org and click on the Give Now button and follow the easy steps. It only takes a couple minutes. If you make a gift, you'll be signed up for our weekly or monthly newsletter, which you can also do on our homepage. So we'll hope you'll head on over to SETI.org. And a big thanks to all of you for joining us tonight. And thanks to our guest speaker. Again, thanks Jade and Joshua and Simon, our excellent moderator. I also want to thank Frank, Lee, and Beth, and Jasmine, and Rebecca, and the rest of the team at the SETI Institute who make this wonderful series possible. And don't forget to visit our YouTube channel and tour all of the lectures and presentations and other videos that are posted there. And again, most importantly, don't just come along for the ride. Join us at SETI.org. Be part of our mission. Join our team. The search for life beyond Earth is a journey of ultimate discovery, and it's one we invite you to join. Thank you all for being here. Have a wonderful evening.